When electrical problems occur, we're called on to fix them fast. And as we all know, trying to do things too quickly can lead to mistakes. Today's high-energy power systems can deliver a deadly blow to anyone who fails to take the right safety precautions. For all of us at Fluke Corporation, your safety is very important. For more than 50 years, you've trusted us to provide you with the finest electrical test instruments. Tools that meet or beat every safety standard. That's a trust we take very seriously. That's why we've put together this program to help you work safely. Working safely while making electrical measurements is not magic. Safety results from a simple winning combination. Careful planning, safe work practices, combined with using the right tools. We urge you to pay close attention to this program. What you learn could save your life. In this video, all individuals shown making the electrical measurements are wearing personal protective equipment consistent with the standards established for the United States by the National Fire Protection Association, or NFPA. NFPA Electrical Safety Standard 70E sets categories of hazard and risk from 0 up to 4. As the work environment and the type of job become more hazardous, the need for protection increases. For example, work on a 600-volt motor control center would require varying levels of protection, depending on the job. Operating a circuit breaker with enclosure doors closed is hazard risk category 0. Required personal protective equipment, or PPE, includes a long-sleeve shirt and long trousers made of natural fiber material, and safety glasses. Performing the same operation with the panel open increases the hazard risk level to 1. Here, you need to add a long-sleeve flame-resistant shirt and heavy cotton pants, such as blue jeans, flame-resistant trousers, or flame-resistant coveralls. You may also need gloves and leather work shoes. Voltage testing on energized parts increases the risk hazard level to 2+. For this job, you need a natural flame-resistant t-shirt under your flame-resistant shirt and natural fiber trousers under your flame-resistant pants or coveralls. You need safety glasses or safety goggles under a double-layer switching hood. Earplugs, voltage-rated gloves with leather protectors, and tools are also required. Insertion or removal of individual starter buckets from the motor control center takes the hazard to level 3. For this job, you need a hard hat with a flame-resistant liner, switching hood, earplugs, voltage-rated gloves with leather protectors, and work shoes. As you can see, as the risk of your job increases, the protection required by NFPA also increases. Keep in mind that these are general guidelines. Some procedures within Category 2 require greater protection, as described on page 31 in the NFPA 70E manual. When you make electrical measurements, safety should always be your first consideration. If you plan your work carefully, follow safe measurement procedures, and use the right equipment, you can cut your chances of an accident to near 0. Your first step is planning. Before you open an equipment cabinet, look over your work environment. Where will you mount your meter and place your other equipment? Be sure to identify a clear escape route you can use in case of emergency. Do you have enough clearance to gain access to the equipment in question and to work comfortably? Are environmental hazards present, such as tree branches or water? Do you have enough light and ventilation? Make sure you have another qualified person to assist you, who also understands electrical measurement safety. It's never good practice to work alone on high-energy circuits. Finally, make sure someone else knows where you're working. Another key part of planning is choosing your safety equipment, tools, and assistance. Make sure you have the required personal protective equipment, or PPE, on hand: eye and hearing protection, gloves, clothing, and insulating mats. Be sure to inspect your equipment to make sure it's in good condition. Check your tools for proper insulation, and make sure your meters and testers are rated and tested for the level of hazard that exists where you're working. Many testers look similar, but make sure you know what yours is designed to do. Then, inspect your meters, testers, test leads, and related equipment to make sure everything is intact and working properly. At the end of this video, we'll show you how to test your meter and test leads. Whenever possible, work on de-energized circuits and always follow proper lockout-tagout procedures. When taking single-phase measurements, always connect the grounded lead first, the hot lead second. After taking your reading, disconnect the hot lead first, the grounded lead second. To make sure your meter is working, use the three-step test method. First, test a circuit you know is live. Next, measure the target circuit. But before you conclude that circuit 2 is dead, retest the known live circuit. This way, you know your meter is working. Try to follow the old electrician's advice. Whenever you can, keep one hand in your pocket, but use common sense. Sometimes you need both hands to make a good measurement. The safest place to measure voltage is where the lowest energy is available. For example, if you're measuring voltage on a breaker panel, identify the lowest rated breaker available and make your measurement there. This way, you have more protection between yourself and the potential hazard. Following these steps will help you work safely. But sometimes, even these steps can't prevent trouble. Switching of inductive loads, lightning strikes, and transmission system switching can generate huge voltage spikes. These voltage spikes, or transients, can last as long as 100 microseconds, but they can be extremely dangerous. In modern power systems, transients are present all the time, some small and some large. But where do transients come from? When an inductive load such as a motor or transformer is switched off, it generates a voltage spike, sometimes called a kickback spike. In some applications, kickback spikes are useful. Your car's ignition system depends on kickback spikes generated by the coil to produce a spark. But when we're measuring power systems, transients and sparks are definitely not good. And here's why. In your car's ignition, the power source is weak and the spark disappears as soon as the voltage does. But in a power system, the system voltage does not disappear, and because the circuit is a high energy source, it can supply current to the spark until the surrounding air breaks down into a conductive plasma, causing a major fault. When transients ride on top of the system voltages that supply industrial loads, they can reach thousands of volts, and the consequences can be devastating, particularly for anyone taking measurements on electrical equipment. In these circumstances, proper procedures alone are not enough. You need to reduce risks by using the right meters and test equipment, tools rated for the environment where you're working, and tested to meet the appropriate safety standards. To provide better protection for electrical workers, new standards have been developed for test equipment used in environments of 1,000 volts or less, including 480 volt and 600 volt three-phase circuits. In the 4-category rating system, the closer you are to the power source, the higher the category, and the greater the danger. Transients in categories, or CATs 3 and 4, can be extremely dangerous. The available fault current in these high-energy circuits can reach as much as 100,000 amps. CAT 4 refers to power lines at the utility connection, but it also includes exterior overhead and underground cable runs, since both may be affected by lightning. CAT 3 covers distribution level wiring. This includes 480 or 600 volt circuits, such as three-phase bus and feeder circuits, motor control centers, load centers, and distribution panels. Permanently installed loads are also CAT 3. CAT 3 also includes big loads that can generate their own transients and are now more common than many people realize. The trend to using higher voltage levels in modern buildings has changed the picture and increased the potential hazards. Most commercial and industrial electricians work on equipment in a CAT 3 or CAT 4 environment. Many times, people may be working in a CAT 4 environment without even knowing it, and that can lead to real danger. Lower category installations usually have greater impedance, which dampens transients and helps limit the fault current that can feed an arc. Cat 2 covers the receptacle circuit level and 120-volt plug-in loads. And Cat 1 refers to protected electronic circuits. Some installed equipment may include multiple categories. This motor drive panel is Cat 3 on the 480-volt power side and Cat 1 on the control side. In these environments, you should use the tools and personal protective equipment rated for the higher category. In general, where greater fault currents are available and as voltage transients increase, measurement becomes more hazardous. This is reflected by a higher CAT rating. National standards for workplace safety include test instruments as part of personal protective equipment. The National Fire Protection Association clearly states that test instruments and their accessories must be rated for the environment where they will be used. If you're working in areas that require personal protective equipment, you're probably in a Cat 3 or Cat 4 environment. You should be using test equipment rated 600 or 1000 volt Cat 3 or 600 volt Cat 4. Let's take a closer look at why transients are so dangerous. In this example, a service technician is making a phase-to-phase voltage measurement on a 480-volt motor supply circuit. This is a Cat 3 environment. A major voltage transient caused by load switching or a nearby lightning strike was large enough to cause an arc to strike inside the meter. Short-circuit currents as high as thousands of amps can flow for several microseconds. At these current levels, the tips of test leads superheat, and the handheld probe tips start to burn away, drawing an arc from the contact point to the probe tip. The tech sees a bright blue arc flash, and at the same time is startled by the bang of the arc exploding inside the meter. The arcs follow the vaporized test probes. If these two arcs join through close proximity of exposed metal from the test probes or other mechanisms, one large arc is formed, providing a low impedance path directly from one electrical phase to another. When two arcs join, they cause either a phase-to-phase or phase-to-earth fault. The result is an arc blast, which can lead to a plasma fireball fueled by the energy in the electrical system. When this occurs, temperatures can reach about 6,000 degrees Celsius or 10,000 degrees Fahrenheit. Industry sources estimate that in the U.S., 5 to 10 arc flash accidents occur each day. The U.S. Bureau of Labor reports that in one recent year, 1,000 electrical workers suffered shocks and burns, some fatal. It is estimated that 50% of these injuries are related to arc flash. This percentage could be dramatically reduced if technicians utilize the combination of careful planning, correct safe work practices, and use the right tools. Here is an actual arc flash. This circuit breaker was designed to interrupt 14,000 amps of fault current, but is intentionally used on a 50,000 amp circuit. A dead short was created on the load side of the breaker.
My name is Ed Manthei. I've been a professional electrician for over 35 years in Eastern Washington, doing primarily commercial and industrial electrical work. About 2.5 years ago, I had a personal experience with arc flash. I heard a buzz, and then after that, a major explosion. I was able to get my eyes closed, I think, and my head back a little bit, blew me back on the floor. Next thing I remember, I was standing in the corner and I couldn't see, and my shirt and stuff was on fire, which I didn't even realize at the time, being as I couldn't see. And me personally, I've always been accused of being too safe, overly cautious, because it's hard to prepare for something you can't see. Make sure that you use the proper safety precautions. I guess the bottom line is you can't be too careful.
Transients aren't the only source of arc flash hazard. In fact, one of the most common misuses of handheld multimeters can cause a similar chain of events. If the user leaves the leads in the amp's input terminals and then accidentally connects the meter leads across a voltage source, he has just created a short through the meter. That's why the amp's terminals must be protected by fuses. These fuses may be the only thing standing between that user and a potential disaster. If the meter is fused correctly, the only result may be a damaged fuse, which is a small price to pay. Never replace a damaged fuse with the wrong fuse. Only use high-energy fuses specified by the manufacturer. The Fluke meter system, which includes the meter's internal circuitry and fuses, and the test probes shipped with the instrument, works together to properly interrupt fault currents that exceed 10,000 amps. Test probes and other accessories can also contribute to danger. Test leads can become frayed or come out of the meter jacks. If the probe tip is connected to 480 volts and a nicked or underrated test lead comes in contact with another conductor, a fault may result. The same thing can happen if an unshrouded test lead comes out of the meter and touches a conductor. Make it part of your routine to inspect your meter and its test probes before using them. Please refer to the guidelines provided at the end of this video on what to look for. Remember, test probes are designed for a variety of test environments. What is appropriate for a circuit board in a Cat 1 environment may not be appropriate for 480 or 600 volt circuits. In a high energy setting, make sure your test probes have a minimum amount of exposed metal. This will help avoid creating a short between two phases if your hand slips off the probes. Meters and other electrical test tools should be independently evaluated to make sure they can survive high voltage transients. A special test machine is used to generate the overvoltage transient and fault current as defined by national and international standards. This meter is marked 1000 volts Cat 3 on the front of the case. More importantly, it has been certified by an independent testing laboratory. A 1000 volt Category 3 tester is required to survive a minimum of 10 transients of both positive and negative 8000 volts without creating a hazard. Fluke goes a step further in designing and building our test tools. We build our meters with safety in mind. In addition, we build them to survive. As a short test, we have programmed our test machine to increase the transient voltage in steps until the meter fails. 6,000 volts. 9,000 volts, 12,000 volts, 15,000 volts, 17,000 volts. This meter finally failed at about 17 kilovolts, which easily exceeded the minimum of 8 kilovolts. Some manufacturers state that their products are designed to meet or conform to standards, but not every meter or tester that makes that claim will pass the test. Here's what happened when one meter, marked 1000 volts Cat 3, was actually tested. The meter is supposed to withstand a minimum of 20 transients of 8 kilovolts each, but this meter failed twice before reaching the 8 kilovolt minimum level. If this had happened on a power circuit, the results could have been disastrous. How could this meter fail the test? The standards bodies only create the standards. They do not enforce them. A meter that claims to be designed to a standard may have never been tested to it. That's why it is essential that the tester you use is labeled to show it has been certified by 2 or more independent testing laboratories, such as UL in the United States, CSA in Canada, and TUV in Europe. This is the only way you can be sure your testers have passed the most rigorous tests and meet every applicable standard. Here's what can happen when a meter marked Cat 2 is used in a Cat 3 environment. In a real Cat 3 or Cat 4 environment, the arc would have been fueled by thousands of amps. The resulting arc flash could cause serious damage to people and equipment. In addition to the right kind of transient protection, a meter should be able to withstand accidental overloads associated with the various functions of the meter. This meter is marked 600-volt Cat2. Watch what happened in this test when it was connected to a live circuit while in ohms. Here's what it does if you measure voltage using the amp's input jacks. The fuse would not protect the meter or user. Just imagine if this meter was in your hand and used on a real Cat3 circuit. Even the most careful of us will make mistakes. That's why, if an inappropriate voltage is applied, your meter should offer a margin of protection. This principle is so important that it has been written into current safety standards. The standards require that test equipment must handle the full meter voltage rating in the ohms and continuity functions without becoming a hazard. To meet the demands of today's high-energy, high-hazard workplace, quality manufacturers have re-engineered their test instruments to make them more reliable and far safer. Safety is the result of a winning combination. Careful planning and the correct safe work practices combined with the right tools. Use a meter that both meets today's standards and is rated for the measurement category and voltage level where you are working. If you use test equipment on or near 480 or 600 volt circuits, you should use 600 or 1000 volt Cat3 or 600 volt Cat4 meters and testers. How does your test equipment measure up? Here are tips for inspecting your own equipment. Look for the Cat3 or Cat4 rating on the front of your meter and testers, and a double insulated symbol on the back. Look for approval symbols from 2 or more independent testing agencies, such as UL, CSA, or TUV. Check the meter fuses for the correct amperage and voltage. Fuse voltage must equal or exceed the meter's voltage rating. Check the condition of your meter or tester. Watch for a broken case, a faded display, or other problems. Check your manual to see if the ohms and continuity circuit is protected to the same level as volts. If the protection level is not listed, ask for written confirmation from the manufacturer. The relevant standards are covered in IEC 61010 or ANSI S82.02. Examine your test leads for such features as finger guards, cat ratings, and double insulation, and look for frayed or broken wires. Check the length of exposed metal. You can use your meter to check for internal breaks in your test leads. Turn to the ohms function. Then, short your leads together. The meter should read close to 0. With the leads still shorted, jiggle the leads and look for an intermittent open circuit, which could signal an internal break. Test your meter's fuses by turning to the ohms function, then inserting your red test lead into the amp socket. The meter should read near 0. A blown fuse would read as an open circuit. Then insert the test lead in the milliamp socket. The meter should read close to 10,000. The actual resistance value will vary depending on the model of meter used. At a minimum, verify that the meter does not read OL. Finally, if you've ever had a blown fuse or mishap with your test instrument, make sure you get it checked out and properly calibrated before using it in a high-energy environment. If your test instrument passes these tests, congratulations. You are successfully managing some of the risks inherent in measuring electrical equipment. On behalf of everyone at Fluke Corporation, Thank you for watching. We hope you share our commitment to electrical measurement safety. While you can't totally eliminate the dangers of working with electricity, with the right attitude and the right actions, you can significantly reduce them. Remember and use the 3 key steps in that winning safety combination: careful planning, safe work practices, and the right tools. What you have seen today is only an introduction to the topic of workplace safety. We urge you to keep learning and put your safety knowledge to work. After all, the one who benefits most from safety is you. Thank you. And from all of us at Fluke, work smart, work safely.
My name is Ed Manti. I've been a professional electrician for over 35 years in Eastern Washington, doing primarily commercial and industrial electrical work. About 2.5 years ago, I had a personal experience with arc flash. I was removing an I-line breaker out of a panel board, and apparently there was an unfused conductor coming off this main lug panel that went up to a voltmeter, and the big conductor that was hooked to this breaker had been rubbing up against that all these years. And when I moved that big conductor, which had a 90 on it, out of the way to get the breaker out, when I moved that conductor, I heard a buzz, and then after that, a major explosion. I was able to get my eyes closed, I think, and my head back a little bit, blew me back on the floor. Next thing I remember, I was standing in the corner and I couldn't see, and my shirt and stuff was on fire, which I didn't even realize at the time, being as I couldn't see. And so I yelled for help, and a fellow electrician came back in the room. Apparently he'd helped me up and left the room and thought I was with him, and he didn't realize that I couldn't see, and came back and got me. They took me outside and put me out with the fire extinguisher, and of course my main concern was I thought I was blind because I couldn't see anything. I was in the hospital approximately 3 weeks the first time, and then they let me go home for a week, and we were still treating my chest and stomach, hoping it would heal on its own. It didn't, so I had to go back, and I was in there another 3 days, and they grafted my stomach. And then I went home, and in another week and a half, all the skin that had healed on my hands, the back of my hands and arms, started to blister. So I went back in for another 3 days. They were trying to figure out what was going on there. Then I went home for approximately 2.5 months and to see if this blistering, sometimes it'll quit. And unfortunately mine didn't. So then I had to go back in and have a 5-hour surgery, taking all this skin off, and then another 5-hour surgery, taking skin off of my legs and putting it on my hands and arms. And then after I recovered from that, the following spring, I had to have this finger removed and the webbing fixed between the fingers. When they graft, the tissue, skin ends up being out over the ends of your fingers, so you have like webbing in there, and they take and remove that and take skin from your side and splice it in there and get rid of that webbing. And then 6 months later, I had to have the end of this finger removed, and the same thing done here, the webbing removed, plus the thumb I had to be relieved because it had healed in tight like that. I couldn't pick up a glass of water or anything. The impact from going through something like this is, and I'll talk about the impact that you don't realize. Fortunately, the medical expenses were covered, but all told, my wife spent 2 months over at the hospital with me. Had to stay in a hotel or facilities when they were available at the hospital. Of course, there was food, all the travel back and forth, all the work she missed, all the work I missed. You know, it's a huge financial impact on you personally, and it impacts your whole family, because now they're making trips over to see you. It's you know, it's just a huge family expense. You know, that's the part, I guess, that you don't realize until you get in a situation like this, where you get hurt bad enough to have to merit being in hospital for 2 months. I don't do anything different now than what I've always done, safety-wise. You know, my advice would be that if you're going to do a project, you know, look at what you got, analyze it, figure out what you're going to need for safety equipment, what you're going to need for meters, what you're going to need to safely complete the project. If you're working on a project and for some reason you maybe you don't feel safe with it, maybe somebody you're working with, they think it's okay, but you don't think it's okay. If you're not comfortable, you need to let people know, and somebody needs to take a look at it. I would like everyone to know that it's extremely important that you be careful at all times when you're working around electrical equipment. As much as you can, look for that thing that might be hidden that you can't see, and take all the necessary precautions to prevent something like this from happening to you.